if we expand this microprocessor structure or the system structure, then it consists of the modules like this is the microprocessor that we have consisting of this ALU, the register array and the control. Then we have got this memory and IO. So, that are the other parts that we will have in the system, and they are connected by means of some bus. So, which is known as the system bus. So, through this system bus, this processor or the microprocessor will talk to the memory, it will also talk to the input output devices. Now, under this we will have this memory. We will first look into this memory, the part that we have, and memory is nothing but a storage. So, it stores information such as instructions and data in binary format, and it provides information to the microprocessor whenever it is needed. So, this is basically some storage that we have, and as I have said that when we compile a program and then load it into the memory. So, this memory is holding that program. So, like that it is a storage part. So, memory is we talk about memory as a subsystem, and in this subsystem we have got registers, ROM and RAM. So, registers are part of the CPU. So, that is inside the microprocessor, but this ROM and RAM, so they are outside the microprocessor and they are as separate chips. Okay. So, the microprocessor actually talks to this ROM and RAM by means of that system bus that we have seen. But from the angle of storage, so all these modules, registers, ROM and RAM, so they are storing some information. So, we will put them under a broad heading of memory subsystem. So, in the memory subsystem all these information are stored, and then it can get the information, the processor can get the information from that part. So, next we will be talking about an important concept which is known as memory map and address. So, as I have said that a memory is nothing but some storage. So, if this is the storage, then there are two questions to be answered, like how are you storing information there. So, I have said that this is in terms of zeros and ones. So, these are the individual locations that I have, individual rows that I have of zeros and ones. So, how many rows are there and how many columns? So, I can say my question is how many rows and how many columns. So, in individual column, so this may be storing the bit pattern 10 10 10 like that. Okay. So, these are the columns. So, this is the first column, this is the second column, this is the third column like that. Similarly, so these are the columns C1, C2, C3 etc., and these are the rows. So, this is the row 1, this is row 2. Okay. So, like that. So, whenever I am trying to access this memory, so it is always done in terms of rows. Okay. So, normally we do not access memory in terms of these individual bits or in terms of columns. So, we will be always accessing a particular row together. So, we will always be accessing a particular row together. Okay. So, it is never that we access a particular bit within a memory. So, it is not that we access a single bit separately. Okay. So, it is not done. So, this entire row is accessed by the processor. Now, if I have got say m rows, then somehow the processor needs to tell like which row it wants to access. Fine. So, to tell that, so it needs to so if there are m such rows, so to identify any row here, so I will need log of m. I will need log of m number of bits to be specified. So, what I can do? So, I can have a decoder where I can say, so I can put a decoder, and that decoder will be, that decoder can find out like where to which location I am talking about. So, it is like this, that if I put a decoder here, okay, and then here I tell what is the, here I put that log m bits, okay, or better I should make a different notation. So, this is my memory block that I have and this is the decoder. So, here I am feeding log m number of bits. As a result, this decoder generates m such enable signals. It generates m such enable signals, and depending upon the value that I have given here. So, one of these lines will be enabled and rest are all disabled. So, it may be that it has enabled it has put this line as 1 and all these lines are at 0. As a result, so this particular row of the memory will be accessed. So, if we look into a memory chip, then we have got these log m lines coming as input, one input, and this is commonly known as the address lines. So, in the address lines you need to tell which row you want to access, and as I have said that all these location, all these bits, so they are available at the output of this memory chip. So, that this is output. So, if this is if the number of columns here is n, the number of columns here is n, then at this point I get an n bit output, and this n bit output. So, they are known as the data lines, they are called data lines. Fine. Now, if it as we know that if it is a ROM, then I can put the I can give it address and I can tell it, I can give it the signal read. Accordingly, this content will be available here. On the other hand, if it is a RAM, then there are two controls, read and write. Now, if I am trying to read the content, then I will give the read signal, put the address here. If I am trying to write something onto the location, then this line is bidirectional in case of RAM, and then I put the value onto this data line, we put the address here and then we give a write signal, so that whatever value is available on the data line gets written onto the location. So, this way we this is the generic structure of a memory block. So, we can say that it is like this. It has got the address lines or A, it has got the data line or D, and it has got some control lines. So, so it has got this read and write controls, and also many of these memory chips. So, they will have some chip select signals CS, and there may be multiple such CS chip select signals, CS1, CS2 like that. Okay. So, and each this memory chip has got some capacity, like it may be say 4K, it may be say 2K. So, this is that is 4K, that identifies it is 4 kilobyte 4 kilo such locations are there. So, if it is 4K into 8 bit, that means individual locations are 8 bit wide and there are 4K such locations, that is 4 into 1024, that is 4096 locations are there in this chip. Similarly, if it is 4K by it is 2K by 4 bit. So, this is 1024 into 1024 into 2K by 4 bits. So, this is 2048 rows and each of 4 bits. So, total whatever be the number of bits coming. So, that is the total capacity of this, but this has got 2048 locations compared to 4096 location here. So, this 2K chip will have 2048 words in it. Anyway, so that we have seen in the while discussing about this memory chips and all. So, in the context of microprocessors, what happens is that every microprocessor will have certain number of address lines and a certain number of data lines. So, it will be coming from the microprocessor itself, and there those lines are fixed. Okay. So, if a microprocessor has got m address lines, then it can access 2 power m memory locations from that, and it has got the n data lines will tell that the memory chip that we want to connect should provide me n bit data at a time. Now, depending upon the structure, depending upon the chips that we are connecting, and then we can have different type of connection. For example, you may say that this is the total address range of the microprocessor. Like here it is said that okay, I have got addresses running from 0000 to FFFF. So, this is true if the microprocessor has got 16 bit address lines, because this FFFF, that means it is a all the 16 bit value. So, this has got 64K alternate values in the address range. So, my microprocessor address bus, the address lines that the microprocessor generates must be 16 bit, and then using that, so it will be able to distinguish between any of these 64K locations. But the memory chips that we have, so that memory chips may not be having 64K capacity in a single chip. Okay. So, so I will need multiple such chips. Also, I need to distinguish between some part of the system. So, some part of the program may be fixed, whereas some part are varying. So, for example, the operating system part of the of the system, so that is fixed. So, that we need to have in some part of the memory. So, normally what is done is that at the beginning of this address range, so we have got this we try to put one EEPROM, and in this EEPROM, so we put the operating system part, and then in the later part, so we try to put the RAM chips. Okay. So, where for that is for the for access for if to be used for different purposes, for storage purpose. So, the first RAM chip that is shown here, so that will be ranging over the addresses 4400 to 5FFF, and the second one, so that will be ranging from 6000 to 8FFF. So, their capacities are not same, but in a general design, so their capacities may be same also depending upon the RAM chips that we put. And between this EEPROM and this RAM 1, so there is some space which is not utilized. So, this address range that is the 4000 to 43FF. So, that part of the address, so that is not used by the processor. Okay. So, so it is assumed that the processor will not generate any address in that range. So, if it generates, then the system behavior is unpredictable. However, similarly towards the end, so it generates address up to F7FF, and it does it from F800 to FFFF. So, this address range is never generated by the processor. So, it is assumed like that the whatever program we will be loading into the memory and the processor will be executing, it will never generate addresses in the range 4000 to 4400 43FF, and similarly from F800 to FFFF. So, it will not generate any address in that range. Anyway, otherwise we can connect it like this. Now, how do you make this connection? So, your I have said that if this is the address lines that we have. So, here I have got 16 address lines coming here, and how these address lines are going to select these individual chips. Okay. So, that has to be seen. So, we will take an example and try to explain that part. So, suppose I have so in the 8085 based system that we have. So, I have said that it has got 16 bit address lines. Suppose 16 bit address lines are named as say A0 to A15. So, they are named as A15 to 0, where A15 is the highest the most significant bit and A0 is the least significant bit. So, from my 8085 chip, so if this is the 8085 chip, so these 16 lines are coming out. Sorry. So, from my 8085 chip, these 16 lines are coming out. So, like this. Now, this is my A0 to 15 that is coming out. Now, in my system total 64K. So, maybe I have got say chips, memory chips of size 4 kilobyte only. So, how do I connect them? So, I will need 8 such chips to I will need, so suppose let us take a slightly larger sized chip. Suppose I have got 8 kilobyte chips. Okay, if I have got 8 kilobyte chips, then for 64 kilobyte I will require 8 chips in that case. Okay. So, what I can do? So, I can put 8 such chips in this way, 8 such chips in this fashion, and for 8 kilobyte. So, the for 8 kilobyte the address lines needed is your 10 plus 3 13 bit. So, 13 bits are the address lines for this individual chips. So, I take this A0 to A12 to each of these chips. To all these chips we put A0 to A12. So, those lines are going there. So, this part is A0 to 12, and the bits 13, 14 and 15. So, they are fed to a 3 to 8 decoder. They are fed to a 3 to 8 decoder, and this output lines. So, they will be selecting those lines, the chips. So, what I mean is that I have got a 3 to 8 decoder here, 3 to 8 decoder. So, the lines A13, lines A13, A14 and A15, they come here, and this is so this first line goes to the first line goes to the chip select of the first chip, then the next line will go to the chip select of the next chip. So, like that. So, what I mean is this first line it goes to the chip select of the first chip, the second line goes to the chip select of the second chip, third line goes to the chip select of the third chip. So, this way the last line will go to the chip select of the last chip. Then what will happen, any address that is produced. So, if it is in the range of 0 to 8k, first 8k, then this chip will be selected and this data will be coming out of this chip. Now, if I sort all these data lines together and feed it to the data line of the microprocessor, then this the location, the corresponding content of the corresponding location will be available to the 8085 onto the data line. Similarly, if the address generated is between 8k and 16k, so then this chip will get selected and this chip will provide the data. Okay. So, via this chip select line, so it is ensuring that. Now, what can happen is that many a times I do not need so many chips. Okay. So, that is I do not so in this previous example, the memory that we connected was also 64 kilobyte in size. Now, it may so happen that in my system I need only 32 kilobyte, I do not need others. Then if I have got say 8 kilobyte chips, so I will take these 4 such chips, and they will be getting the lines, address lines A0 to A12 as we have seen previously. So, they will be getting the lines A0 to A12. Now, for differentiating between 4 chips, so I will need a decoder which is a 2 to 4 decoder. This is a 2 to 4 decoder. So, this decoder it will get the lines A13 and A14 from the microprocessor address lines, and then it will be generating the chip select signals for them. They will be generating the chip select signals for the individual chips, memory chips. Now, so what happens for the address range, for the addresses in the range which is more than this 32k. So, here it is implicitly assumed that we have got this A13. So, the bit A15 is taken as 0, and this is the size A14 to A0. So, that will determine what we are going to, which chip we are going to access. Similarly, this A15, if this A15 is equal to 1, then also if you give some value, so A14 to A0. Now, suppose these two contents are same. So, this content and this content are same. So, you can understand that since this whole design that we have done, it is independent of the bit A15. So, in both the cases it will access the same location. So, it will access, if the address range A14 to A0 is such that it falls into this chip, then in both the cases A15 equal to 0 and A15 equal to 1, it will be accessing the same chip. So, this phenomena is known as memory folding. So, this is known as memory folding, that is for the same for different locations. So, if it's different addresses, it is accessing the same memory location. So, this may or may not be desirable. So, in some systems, so if the memory folding is there, so I cannot expand the system, because now I cannot put further chips here, because the pin A15 has not been used at all. And if you can say that, so how to stop this folding? So, folding can be stopped. Many a times what happens is that this 224 decoder, so they have got some enable line, as we know. So, it has got an enable line. So, if it has got some enable, then we can use that enable line to stop this phenomena. Okay. So, we can put an inverter and connect the A15 line here. So, that means when this A15 equal to 0, then only this enable line will be equal to 1. As a result, this decoder output is enabled. Otherwise, this decoder will be in a tri-stated state. So, it will not be selecting any of these outputs. All the outputs will be in 0 state. Now, so none of the chips will get enabled. Now, if A15 equal to 0, then only this enable signal is high, as a result appropriate memory location will be selected. So, this way, so this is this address does not have any meaning, okay. In this case. So, if A15 equal to 1, then none of the memory chips will get selected. So, that location is not within the addressable range generated by the processor in that case. So, that way memory folding can be resolved. But of course, if you are not bothered much, then you can definitely allow memory folding, because if you allow memory folding, then this extra logic gate, this inverter and all are not required. Similarly, it may so happen that you can work with a simpler decoder that does not have any enable line in it. So, you can directly use a chip which is a decoder, but does not use the enable line, whereas in this case you need to use a decoder where it has got an enable line. If we are avoiding memory folding, then the advantage is that later on, if you want to expand the system by putting another chip here, then you can have another decoder, and for that decoder you take the enable line and connect it directly here, fine. So, and this chip or this decoder output say give chip select to the lower chip. So, that as a result what will happen is that this block will be selected only when A15 equal to 1. So, you get the addition. So, you do not need to generate, you do not need to expand this decoding logic by putting putting a larger decoder, but you can just extend the design. You can just put another 2 to 4 decoder here, okay, and then from by using this enable line. So, you can enable that decoder, and the previous decoder. So, it will be valid for the upper 32 kilobyte, and this decoder. So, this will be selecting the lower chip. So, this way for memory expansion purpose, it is better that we have got this memory folding resolved, so that we can expand the system later. That will not be possible if we are not using memory folding. So, if we resolve it previously, so if we allow memory folding, then of course, this cannot be done. Okay. So, another possibility that we have is that this memory chips, so it may not have the data line may not be sufficient. For example, maybe I require some a memory of capacity say 32 kilobyte. Okay. So, these individual chips that I have are say 8 kilobyte, it has got 8 kilobyte location, but 8 kilo locations, but individual locations are of 4 bits wide. So, this we have seen previously that we have got 8 kilo and 4 bits. So, this is 8 kilo by 4 and this is also. So, what you do in that case is you take 2 such chips in parallel. Okay. So, we have got this is another 8 kilo by 4. So, total 32 K. So, this is 8 kilo by 4 and this is another 8 kilo by 4. So, you take another such chips. Fine. And then from the processor side, okay, so this is a 8085, the address lines, then the decoding and all. So, this address lines A0 to so 8K, so A0 to A12, so they go to individual chips. So, A0 to A12 is connected. So, we are making connections like that. So, these address lines A0 to A12 are connected, and then from the decoder, if this is my decoder, then this is the lines so if this is the decoder, then we have got the, so this is A0 to 12, A0 to A0 to A12. So, this is A13 and this is A14. So, they are so from this I generate the decoder signal, and this chip select line goes to both the chips. Okay. So, this chip select line, it goes to both the chips which are in parallel. So, here this one, this next chip select line, it goes to both the chips which are in parallel, third one goes to both the chips in parallel, and the fourth one again goes to both the chips in parallel. So, what happens is that if this decoder is selecting one chip, so this is actually selecting a pair, and then for the address bus, what we do, if this is for the data bus, what we do is that this will give me 4 bits and this will give me 4 bits, and they will be connected to the 8 bit output. So, this is, suppose this is an 8 bit data bus or 8 bit data lines for the processor. So, first most significant 4 bits will be coming maybe from this memory, and the least significant 4 bits will be coming from this memory. So, these lines, so they will be connecting to the data line D0 to 3, and these lines they will be connecting to D4 through 7. So, everywhere it is like this. So, this is connecting D4 to 7 and this is connecting D0 to 3. So, this way we can make the other connections. So, this way you can make a memory system which is using the basic memory chips of different sizes as it is available, and then we can connect them in some fashion by means of this decoding logic from the processor to get the full memory system implemented.